Hi everybody, welcome to our next topic in 12U physics. Today what we're going to be looking at are the forces in circular motion. So if you remember from yesterday's lesson, what we learned about was the acceleration when an object is undergoing acceleration. And if you remember that we had the centripetal acceleration for an object in uniform circular motion given by this expression here. And again, just to remind you, uniform circular motion means that the object is traveling at a constant speed, which means its velocity is changing only in direction. And so we have this as our acceleration, and the acceleration is directed towards the center of the circle. So all we really want to look at today is the forces that are involved in that. And so hopefully you know that if this is the acceleration, then there must be some of the forces given by ma, which in this case can just be written as mv squared over r. Or, of course, since we talked about centripetal acceleration in terms of period, which is t, or frequency, which is f, we get this expression, which again is just the expression for centripetal acceleration, but we also have mass involved. So a mass here, a mass here, a mass here. And that's really the end of the sort of the new contents. But the applications of this are pretty neat. So we're going to talk about some of those today. So the first thing is we did talk about objects traveling around in a circle for the last lesson. And what actually could be causing this are all sorts of different forces. So for instance, in gravity, gravity causes centripetal acceleration quite often. If you take a look at our universe, most things travel in somewhat circular orbits around something else. So one example again is our Earth orbiting the sun. So if we have our sun kind of in the middle here, and we have Earth somewhere else over here, it's going to travel in nearly, well actually it's an ellipse, but for right now let's just say it's a circle, and that means that there's a force drawing it towards the center, and guess what that force is? Well, it's gravity. And it's directed straight towards the sun at all times, which means this is going to accelerate in a nearly perfect circle, and that force, gravity, will be causing the centripetal acceleration. You can also think about tension. If you imagine tying something to a string and swinging it over your head, you've got a circle going on there, and what's actually causing that object at the end of the string to go around? It's the tension force. So tension force causing an object to travel around in a circle. Another one that's quite common is the normal force. So one of the most prevalent examples, or at least the fun examples, would be a roller coaster. So if you're traveling on a roller coaster, you know that the normal force is the apparent weight, and that's that force kind of the seat pushing you. And if you go around in a whole loop-to-loop, so someone kind of like this, what's actually pushing you towards the center of the circle here, yes, it's partially gravity, but it's also the normal force from the seat underneath you. Because again, you can see here that gravity, if you're on this part of the track, wouldn't actually push you towards the center. So the centripetal acceleration comes from the normal force. Another one that's really important is friction. And so if you imagine a car taking a corner, so a car just turning around in a corner, there is no other force that's going to cause that car to turn other than the friction of the tires on the wheels. Pardon me, of the tires on the road. And so that means that friction is actually supplying the force that causes the centripetal acceleration. So here's just kind of four common examples, but just about any force could be causing the centripetal acceleration. It's just whatever is causing this object to move around in a circle. So as I said, the applications of this are kind of neat. So let's take a look at a couple examples. So the first one I have, let's imagine that you're on a roller coaster and that you're traveling around a corner. So we have this roller coaster with a tight horizontal turn, and the roller coaster is traveling at a constant speed of 20 meters a second, and you're actually holding on to your cell phone. I looked up some common values for some of the newer, larger cell phones, and so 180 grams is an uncommon. Um, and so this roller coaster takes a tight horizontal turn of radius 8.2 meters. And just to be clear what this is actually measuring, if we imagine that the roller coaster is kind of a top-down view, this is the path of the roller coaster, well then this section where you actually have the turn happening, if we imagine completing this circle all the way around, this radius here, this would be the 8.2 meters. So this distance here is the 8.2 meters. And so that's kind of the radius we're talking about. So there's a couple things. The first one is I wanted to know what magnitude force must you apply to your phone to prevent losing it out of the cart. So let's imagine we're looking at, let's say, this section right here. So we're going to focus right here, our attention. If we have a free body diagram for your phone, what kind of things we can expect? Well, here's, let's say, your phone. You're holding it, and you're applying force to it. And remember that if it's right here, centripetal acceleration will be forcing the phone this way, which means you have to be applying force in this direction. And if we're looking at it top down, there are no other forces acting on it. So there are no other forces on this plane. It's just you hopefully holding this phone. And we want to know again the force you have to apply to hold it. So let's do a little calculation here. So we know that the sum of the forces has to be equal to ma, and this is centripetal acceleration, so we can actually just talk about what we did the other day, and so this is equal to then m v squared over r. For our v, again, we're using our 20 meters per second. For our r, we're going to be using our radius of this turn, which is 8.2 meters. And again, I trust you can do some number crunching here, but I'm getting a force of 8.8 newtons. So you might be saying, okay, well, that's fantastic, but how much does it actually relate? So let's look at that number, or that force here, compare it to the weight of the phone. So if you were to hold the phone on still, level ground, what kind of force do you have to apply? And again, if we take a look at B, free body diagram, now we'll look at it from the side as opposed to top down. What forces are acting on it? Well, we've got, hopefully you can see, we've got the normal force of you holding it, and we've got gravity pushing it down. And if we're talking about it holding steady, then we know the force has to be equal to 0. So these forces, the force you're applying, we'll say Fa, has to be equal in magnitude to the force of gravity. So again, that means that Fa in this case will just be given by mg. And again, I trust you can do some calculations, but I'm getting for the applied force 1.8 newtons. So let's just pause for a second and think about what that means. So that means if you're holding that phone, again, just standing on the side of the track waiting for your friend to go or something, you to hold that phone takes 1.8 newtons. But to hold that phone around the corner, you have to apply 8.8 newtons, which means you're applying almost 5 times more force when you're around that corner than just holding it. So that I think is something substantial. And hopefully you haven't had this happen to you, but you know, if you don't apply this force, this phone would keep going in a straight line and it would actually fly out of the cart and you'd be without your phone. So again, that 5 times there. Okay, so there's a kind of a simple warm-up question. Let's look at something else here. So as I said earlier, one of the cool applications here is we have a car taking a corner. So here is the example here. You've got a car making a left-hand turn. And it's going around this corner, and we're going to assume that everything's nice and good good traction, and so this car's not slide around the corner, so it's not going to fishtail or spin out. And we want to know what sort of friction is required to actually make that happen. And then we'll look at it again. We'll compare this to some known values for, at least range of values for tires on roads, and see if this number is sort of meaningful. So we have this car traveling at 13 meters a second around a corner. And again, just to give you an idea, 13 meters a second is around 50 kilometers an hour. So this might be a common sort of corner in a residential area where the speed limit is 50 kilometers an hour. So here's this car. The radius of the curve again is 22 meters, and we want to know what sort of force. So again, if we draw a free body diagram for this car, here's the car here. Again, let's take a look at a top-down view. And we'll take a look at it right when it starts the curve, so right around this section here. Then we know the force has to be this way. There has to be some force that way. We know the sum of the forces. Oops, let's try that again. The sum of the forces has to be equal to MA. And we say, okay, what force is actually applying this? What is causing this force here? Well, again, if we think about the top-down view, we have no force really pushing it forward because we're traveling at a constant speed. We have no real force pushing it back. I mean, we can talk about air resistance and engine force, but at a constant speed, let's just ignore them for now. And so hopefully you can see that this force actually has to come from friction. And since we're saying we don't want this car to slide, we're going to be talking about static friction. Because again, we don't want these tires to slide across the surface of the road. We want them to roll continuously so no part of the tire actually is rolling, or sorry, is sliding on top of that road surface. So really, our equations comes down to the force of static friction just has to be equal to mv squared over r. And again, if we want to know the minimum static friction, what that means is we're going to be looking for the maximum value for friction. We want to get the most out of friction as we possibly can to realize what our minimum static friction coefficient needs to be. So in a top-down view, again, we can figure out our static friction max. And again, we understand where that static friction comes from. If we, again, look at, we should label this here, this would be a top view. If we look at a sort of a side view of the same car, and another free body diagram, again, we now have other forces on it. We've got gravity pointing up, we've got static friction pointing left, and we've got, or sorry, gravity pointing down, the normal force pointing up. And so that means this can be our force of normal, this can be our force of gravity, and then this will be our force of static friction at the maximum it can be. So we've got those there, great. And we know the relationship, hopefully you remember from earlier stuff we did, that the force of static friction max is just given by mu s Fn. And in this case, we can say that the Fn and the Fg need to be the same value. And again, hopefully you can see that because the sum of the forces in the y direction, that means the forces going up here, is going to be actually equal to 0. And we know that because vertically, this car is not accelerating. It's not going off of the road. It's not going into the road, so that means these have to be the same. So we can summarize this then as just saying Fs max is equal to mu s mg. All we're going to do now is combine these two equations, and we're going to come up with an expression that says mu s mg equals mv squared over r. Oops, over r. Let's erase that right there, pardon me. And do a little bit of rearranging, and again, I'll leave that to you, but I end up with mu s is equal to v squared over gr. Notice something kind of neat here before we put numbers in. The mass is canceled out. So actually, the maximum sort of speed you can go around a corner doesn't depend on the mass of your car. What does it depend on? Well, it depends on the speed, and it depends on the radius of the curve. So whether you're in a truck or a smart car or a motorcycle, so long as you're going around at a constant speed and the radius is constant, all that really matters here is the coefficient of static friction. So again, do a little bit of number crunching, and I'm getting a number of around 0.78. And that's actually not an uncommon value for US between tires and road. That would actually mean you're at the bottom of the common values. You can actually get upwards of just over 1 for these values. And so traveling around this corner at 13 meters a second would actually be a relatively safe speed to go around this corner. Again, going much faster, and you notice we'd be going up. And notice something else kind of neat here. This is a squared relationship. So if we double the speed around the curve, we actually need 4 times the coefficient of friction to actually make us go around it safely. So speeding around a corner is actually something that's generally not a good idea. All right, so there's that one. Let's take a look at sort of a similar problem, but this time let's pretend that we have an incredibly icy road. So the same sort of road, same 22 meters, but now it's so icy that we don't have any friction. So we're saying that it's like traveling on sheer ice. And I want to know, can I go around this curve safely? If you think about our expression for the last one, you should realize the answer is no, if the road is flat, and the same situation applies. But notice I've changed it. We're actually looking at this road is on a bank. And again, most roads in public roads aren't banked, but some places you might see them. Again, on racetracks, you might see bank curves. Or actually on highway entrance and exit ramps, you might also see banked curves. So these are actually useful, and you'll see why in a second. So what do I know here? I want to know the maximum safe speed for a car on this curve. So if you're traveling on this curve and it's incredibly icy, what sort of speed would be safe? So let's go through again the same sort of analysis we did before. Start with the free body diagram for this car, and we'll start with this car actually traveling at a banked angle, right? So we've got this sort of idea here. We've got gravity pointing down. We've got the normal force pointing off of the surface, and we have centripetal acceleration needs to be in this direction. We might say, well, what is going to be causing this? Because there's no friction, we can't have another force here. We can't stick a force here and say that's got to be friction. So what is causing that? It's actually the normal force. It's a component of the normal force pointing in this direction. And so what we want to do is look at, again, a free body diagram and break it down into components and see what sort of forces are required here. So what I'm going to suggest for our coordinate system is one that has this sort of idea. So we're going to have this as our positive x, and this will be our positive y. So this is going to be the coordinate system that I'm going to suggest for this problem. Again, you don't have to necessarily use this one, but that's what I'm going to do, so you can follow along with what I'm doing here. So here's my coordinate axis, so I'm going to break down. This force is already along the y direction, so I'm great. I guess I should label these. This is Fn, this is Fg. So I'm going to leave Fg as it is, because again, it's already in the direction I want. It's along the negative y direction, but I want to break the normal force into its components. So I'm actually going to have a component that goes up this way, and I'm going to have a component that goes along this way. And again, where is this theta popping in? Again, I can use some hand-waving arguments right now, but if you're interested in the mathy sort of way of proving it, where is this angle theta that the car is tilted at? Well, it would be, again, if I, let's do it in another color so we're not confusing. This sort of thing here, this angle here, that would be theta, but also this angle here would be theta. This one up here between the normal and the and our y direction for our coordinate system. And so if I do that, what that means is if this is our angle theta, this vector over here, the perpendicular, or sorry, the y component vector is just given by Fn cos theta, and the vector up here is just given by Fn sine theta. And again, the neat thing here is that this vector here, this is the one that's actually providing the centripetal acceleration. We know that because it's the only force that's acting left to right, and this car has to travel to the left in this picture here, right? So it's got to go, or sorry, it's got to have an acceleration in this direction. So we know that's got to be the force that actually applies it. So how do we actually figure that out? Well, let's look at our sum of the force statements again. So the sum of the forces will start in the x direction. That is where the acceleration is, so that has to be equal to ma. And so what we just figured out, that's going to be Fn sine theta, and that's going to be equal to m v squared over r. All right, so it looks like we have too many unknowns here because we're trying again to solve for v. We don't have mass and we don't have the radius. Or sorry, we don't have mass and we don't have the normal force. We have to look at something else. Well, let's look at the sum of the forces. It's in y direction. Again, that's up and down out of the road. And hopefully, again, you can see that if this car is not spinning out or flying into the air, that this has to be equal to 0 since there's no acceleration in that direction. And so the forces here, again, using this as our system, that means that Fn cos theta is going to be equal to Fg. Again, because Fn cos theta minus Fg has to give me 0. So let's do a little bit of rearranging and substitution. So then Fn is equal to mg over cos theta. All I'm going to do again is take this Fn, sub it into this Fn, and again do some rearranging here. I'll write the first line. So that means we're going to have mg over cosine. Oh, geez, that's terrible. Mg g over cosine of theta times sine theta is equal to mv squared over r. So a couple things to note here to make the rearranging a little bit easier. One, sine theta over cosine theta. This is probably the most important and the most basic sort of trig identity, is equal to the tan of theta. So that's going to make our life a little bit easier because then it only gives us 1 theta as opposed to 2. The other kind of neat thing here again is, once again, the mass cancels out. And that's something pretty cool and something pretty significant. So again, I'll leave a little bit of the work to you, but I'm getting for my v then is equal to the square roots of rg tan theta. So what does that mean? Well, let's plug in our numbers here, and that means that I'm getting a speed of 8.9 meters per second. So what that means, again, we found this speed. This is the safest possible speed, or sorry, the fastest, let me try that again. This fastest safe speed to go around this curve. And again, we base this curve on having no friction. So a perfectly icy exit ramp from a highway, let's say. And so we can go at 8.9 meters a second, which is not a terribly slow value for icy driving. That's around 30 kilometers an hour. So again, I think that's something pretty realistic. And again, just quickly before we leave this problem, let's look at our end behaviors. So what I mean by that is, well, let's look at what happens if we take these to the extreme. So let's pretend we have no banking on this road. That means theta would go to 0 if we had no banking, because it's a flat road, and tan theta is actually 0. So what that means is, if there were a perfectly friction-free road, there is no safe speed. The safe fastest speed would be 0, which means you can't navigate that corner. And again, I think that makes sense. If we take it to the other extreme and say, let's pretend that this road is like 90 degrees banked, what happens? Well, you actually get the tan of 90. Your calculator is going to say error, but if we take it like as the limit as theta approaches 0, or sorry, as approaches 90, we'd be getting infinity. So what that means is you could actually go around this thing as fast as you wanted to, and you'd never slide off. And again, I think that makes sense, just because if you imagine what sort of force would be causing you to leave because the road was in the way. So I think that's some relevant discussion there. So one last example for you guys. Let's do another one that's kind of fun. I don't know how many of you guys have been on a similar ride at the fall fair, but lots of fall fairs have these rides. So the Starship 3000 has one like this. Wonderland has one called Nightmares. It's kind of similar. But this one, we've got a drum. So you've got kind of the circle, and people are going to stand inside of the circle here. So we're going to have the people kind of as dots around the outside of the circle. Each red dot here I'm representing as a person, and you stand with your back on the wall. And what happens is the ride is going to start spinning around in a circle. Um, and so this ride spins around in a circle very fast. The neat thing about this ride is that eventually the floor drops down. So if you imagine you're in the ride, it looks like you're just kind of stuck to the wall, and you're not going up or down. You're just kind of floating there, stuck to the wall, and that's kind of neat. So we want to know again what sort of speed do we need to ensure so the riders don't fall down onto this floor. And the value I've given you here is the coefficient of static friction between the riders and the wall. And I've also told you this drum is 10 meters in diameter. So from here to here is 10 meters. So that means the radius of this thing is going to be 5. So we know the radius of this thing spinning is actually 5 meters. And we know that mu s is equal to 0.86. Okay. The reason we're looking at static friction here, not kinetic again, we want to make sure they don't fall, so the rider shouldn't be sliding against the wall of this drum. So let's take a look at again at a free body diagram for this example, and let's take a side view. So imagine you're in the ride looking at your friend who's beside you. What sort of forces would be acting on them? And so here's your friend, they're a box, and what sort of things are happening? Well, we've got, of course, these sorts of forces acting on them, right? We've got gravity pointing down. We've got this force, which you might think at first glance is the normal, but let's be careful here because normal is always perpendicular to the surface. So if this is my wall, right, this is the wall of the drum, the normal force is actually this way. So let me label these forces here. So this is Fg, this is going to be Fn. And you might say, well, there's got to be a force to balance gravity up because we want to make sure these riders don't slide down the wall. But what is providing that force? Well, believe it or not, that's friction, right? Because if friction wasn't there, you'd be sliding down this wall, and friction, we know, tries to oppose motion. And so we're going to be talking about friction here, and this is static friction. And again, because we want to know the minimum speed, that means we're looking for the most friction you possibly give us, so we're looking for the maximum static friction here. And so what can we do with this? How can we possibly figure this out? Well, again, just like we've been doing for the last couple of times, let's set up our sum of the forces statements. And so in the sum of the forces in the y direction, I never gave a coordinate system. I think it's probably obvious, but let's say this is y and this is x. So the sum of the forces in the y direction should be equal to 0 because our kind of whole point of doing this is to figure out what speed we need for the riders don't fall. So we want our vertical acceleration to be 0, which means that Fg has to be equal to Fs max. Or another way to write that is mg has to be equal to Fn us. Okay, so that's great. And let's look at it now. I think that's all we can do for this one. So let's turn our attention to the x direction. So the sum of the forces in the x direction has to be equal to, this is where the acceleration is going to come in. This is centripetal acceleration that's causing this person to be forced towards the center of the drum. And so we can write this as Fn equals mv squared over r. And again, so we're looking for this v. We know r, we know mu s. We don't know what Fn is. So let's do what we did before. Let's sub in this value for Fn into this expression here. And what I'm going to get then is mg equals mv squared over r times mu s. And again, notice something pretty neat here. The masses cancel out. So it doesn't matter how big or small a person is on this ride. The same speed is the same, or the minimum speed is the same, and that's something good for ride designers because they don't have to tell the people, okay, if there's large people, spin it faster, and if there's skinny people, spin it slower. So that kind of makes sense. So again, I'll leave some rearranging to you here, but I'm getting for a v the square roots of rg over mu s. So you plunk in the numbers we have, and I'm getting a minimum safe speed for this ride of 7.5 meters per second. So again, if you want to design this ride and you have this sort of friction between people and the walls, you need to be spinning it this fast before the floor drops out. And once it does, you can drop it out all you want and the people won't move. Okay, so I think that's about it for the work examples I have for you guys. I would like you to do one thing for me for tonight before you come to class tomorrow. And I'd like you to go back to the CD example from last class where I calculated the centripetal acceleration for you. And let's assume that the mass of, let's say we have a 1 sort of gram piece of the CD that's added there. So that there's right on the edge of the CD, we have a 1 gram, square, CDs are circles, a 1 gram piece that's added to it. So right around, let's say here, I have a 1 gram, I don't know, dirt particle. What sort of force would it experience while the CD is up at speed? So that's it for tonight, guys. Hopefully you found this exciting, and I'll see everyone in class tomorrow. Have a great night.